Yeah. The only person that got to try to hated it. He's not even a part of it. I don't remember anything.
What?
She'll probably talk to me about it in Kim.
Wait, who did I just notice then?
I don't know.
Did you pick a random?
Yeah.
Okay, I feel bad for.
We don't know anything for that.
Yeah. How much XP do you think?
Okay. I know that's what you're saying. That's what you're
I feel bad, but it's still
But I'm glad that we did that. I didn't really that in second. I'm glad he was.
He's like 10 years older.
I don't know, Molly's so nice.
Yeah, that's so weird. He's 10 years
It
older.
kind of bothered me though when I know.
Why would he never the king? She never had.
Oh my God. Why? I don't know. I'll have to know. Yeah, we actually, just like, and life. Yeah. I know, I don't like that part of it. I just, congratulations. Thank you. There are, I can't do your oh my God. There are 6 people. Wait, that's insane.
Hey.
Cool.
So I have 3 series on the board. You don't need to write it down. Yeah, you want. I just want you to tell me if they convert with either. Quote unquote, yes. As far as you know.
No.
So you can get out.
Hmm?
You got that.
Yes.
You can get out.
Okay.
Today's the last day.
Is it really?
Yeah. She is the
Yeah, I heard you talking to me about it, and I was like, shoot, I'm messing you.
I was like, you go. I emailed Julia like 2 weeks ago. I emailed you, like, oh yeah. I remember having a conversation with you, like through a Zoom meeting.
Yeah.
But I just assumed it was right. Convergence, you want to number? No, you don't have to. Not for this. Not me. Is everybody done? Yes. You can do these. Probably each one of these theoretically could take you less than 10 seconds. It might take you longer to actually write it down than it would be actually figured. Because it takes a while to write those signals. What's that? Sigma? Yeah, it's a Greek letter, capital S. It's a capital sigma. Well, it's a Greek letter that makes the S sound. And that's an uppercase one. A lowercase one looks like this. Okay, so you ready? First one, diverges. It's geometric. Okay, that's geometric with R bigger than 1, right? You could also say the nth term test. I mean, the geometric series tests that when you diverge in geometric, you could also use the nth term test. Number 2. Diverges. Why? The nth term test. Because when I do this limit, I get 1/3. Okay? What does that 1/3 mean? The conclusion is that the series diverges. But what does 1/3 represent? The terms are approaching 1/3. Okay? It's really important that we make that distinction. Okay? And lastly, I tried to trick you. It's geometric. And the common ratio is less than 1 because pi over 4 is actually less than 1. Isn't it? Pi is about 3-ish. 3-ish. It's about 3 and some change. 0.14. So does that that one converges? R is greater or less than 1. And then Abdel said, do we have to find what it adds up to? Let's go ahead and do that together, right? So this one's a converger. Okay. R is less than 1. So what's the first term? 10 over 1 minus pi over 4. Okay, that's. I mean, we don't need to simplify that, but that's what the sum would be. Okay. Question? We got that. So let's talk about the 2 problems I wanted you to do last night. Did anybody discover the magic?
I forgot how to find A and B.
Oh, so you were pretty much struck out at the first bit.
Yeah.
Did you just, so those of you that did find A and B, did you discover the magic? Maybe? Ross, would you have a question?
No, I'm just, I kind of found it.
You think you found the magic? Okay, so let's start with the one at the top. So what was that series? I forget. N squared minus 1. So that's A over N minus 1 and B over N plus 1, right? I factor that denominator. So tell me what A and B are. So this is what Megan said she doesn't remember how to do. So we figure, okay, so we look at this dude here, say, all right, what makes him 0? 1. So then we go over here and we cover this guy up and we plug in 1 for N. And what do we get? 1/2. So that's A. So that's 1/2 over N minus 1. And next one, what makes him 0? -1. So then we do this and cover him up, plug in -1, and what do you get? -1/2 over N plus 1. Yes? So then I can actually, you could leave it like that, but the magic will probably reveal itself a little easier if we do this. That makes sense? And you could even, if you really wanted to, you could do this. Distribute the 2's. Okay? So this is now my series. Okay? Makes sense? Okay. Where did it start? N equals dos? You said 2? Okay, so here we go. Let's write, tell me what the first term is. If I plug in n equals 2, what do I get here? 2 times 2 is 4 minus 2, 2. So I get 1/2 minus, plug in 2 here. 2 times 2 is 4 plus 2, 6. Plus, okay, let's do n equals, n equals 2. N equals 3, ready? 2 times 3 is 6 minus 2, 4th. Minus 2 times 2 is, I'm sorry, 3. 2 times 3 is 6 plus 2, 8. Next one, n equals 4. 2 times 4 minus 2. So that's 1/6. Minus 2 times 4 plus 2. Let's do one more. What are we on? N equals 5. So this is 1 over minus 1 over 12. See if we can see the magic. Does anybody see the magic? So look here. I got negative 1/6 here, and I got positive 1/6 here. I got negative 1/8 here, and I got positive 1/8 there. What's going to be the next term? A positive 1/10. And I add him to that negative 1/10. What's going to happen to that 1/12? Right? All of these terms down after this are going to disappear. They're going to go away. The only thing that you're left with that doesn't go away, that doesn't have a do it, is this in and this in. See that? 1/2 and 1/4 is 3/4. Okay? This is called a telescoping series. The reason why it's called a telescoping is you ever seen those like telescopes like that? It's like you've seen in cartoons where they like extend out. Not like a real telescope. It's like they collapse in on themselves. That's why it's called that. Because that series kind of collapses in on itself. Now that's not easy to recognize. I mean, that's why I told you to skip it initially. What were the A and B's for the next one? The one down below, do you remember? Did you figure them out? Well, what was the one below? What was the series at the bottom?
1 over n times n plus 3.
1 over n times n plus 3. So if we figure out A and B here, so figure out what A and B are. So we have to know how to do this, Joe. It's like we don't just chuck it out the window. So what makes him 0 is 0. So A is 1/3. What's B? Negative 1/3. So then when I rewrite this, that's 1 over 3n plus negative 1 over 3n plus 3. Because that's 3 times n. So, whoa. Sorry, not 3n plus 3. 3n plus 9. Because 3 times n plus 3 is 3n plus 9. That one's going to take a little bit longer, I think, to telescope. But you can sort of see, if you're thinking 1 over 3n minus 1 over 3n plus 9, do you see how eventually you're going to be taking away terms that already appeared? Okay. So those are called telescoping series. Fun little experience to have. Questions on that? How do you recognize that? I mean, how do you recognize that that happens? Basically, if it can be factored like that, and you can break it into the partial fractions, that's where it happens. They take a while to sometimes figure out what the sum is, though, because like this one, you got to write out several terms before you're going to see it. There's other ways. In fact, today, as a matter of fact, if not today, then on Monday, if I just ask you whether or not this series converges or diverges, you'll be able to just look at it and tell without actually determining if it's telescope. We're actually going to set the table for that today.
Does it converge or diverge?
Well, both of them converge because they added up to something, right? I mean, all those, you write down a 1/6, and then down the road, you wrote down a negative 1/6, and then down the road you added on a 1/6. So all those terms disappeared. Yeah, both of those actually converge. But like I said, we're going to learn how to determine that those converge without having to see that they telescope. Telescoping, I mean, that's kind of painful. Painful is maybe strong, but it takes a lot of work to show that telescopes. Okay, so we ready? So we're going to learn about the integral test today. So consider this guy right here. This is a strange beast. 1 over n. So there's a series. Does that converge or diverge? Does anybody know? Tennis match. Is that geometric? No. Okay? So that's not geometric. So our next option is the nth term test. Okay? And what happens when I do that? What do I get? 0. What does that tell me? Okay? It tells me that the terms are approaching 0. That's it. It doesn't tell me anything else. It tells me that it has a chance at converging. Okay? But in this particular case, it doesn't. The chance was very small. Okay? This series actually diverges. All right? We're going to prove why in a second. This, I think, was an example I did in the video. Anybody remember what it was called? What this series is called? Yes, yes, the harmonic series. Okay. This is called the harmonic series. Okay, that's probably a term you probably should be familiar with. It's the harmonic series, 1 over n. We're going to prove right now that it converges. I mean, that it diverges. We're going to prove right now that it diverges. Okay. I saw a hand before. What was the hand? Yeah.
I thought if it was approaching 0, it converged.
The rule for the nth term test is that if it's not going to 0, it diverges. That is not the same thing as saying if you do approach 0, you converge. Does that make sense?
Yeah.
It's like the rectangle square thing. Same kind of idea. Like, if you're not approaching 0, you diverge. That does not mean that if you do, you converge. All right? And that's why it's so important that when you do that limit, you understand what the answer to the limit is and also what you can conclude from that. The answer to that limit was 0. But what can we conclude from that? Nothing. Because that's how the nth term test works. There'll be other times where we get an answer to a limit that's 0 that you can conclude something. All right? So that's why important you got to make sure you understand both pieces of it. So this is the harmonic series. He diverges, and we're going to prove it right now. Okay, here's how we're going to prove it. I'm going to compute this integral. If that integral were representing an area, could you sketch what area that represents? Do that. If that integral were representing some area, could you sketch the area that it represents? Now, I guess you need to know what 1 over x looks like. Sad that you just don't know that off the top of your head. But I'll draw it for you. 1 over x looks like this. It makes that noise when you do it. Right? So what area is this? What inner area is this representing? The area from here at x equals 1 and then to the right of that, forever. Right? Remember that? Anybody remember what kind of integral that's called? What we called those? I can't remember when we learned that. I know we did. I want to say it was right before the first semester exam. Or for the Calc 1, not first semester. Well, yeah, I guess first semester, even though they did it after Christmas. Remember what they were called? Del thinks he knows.
Is it like asymptotic?
Well, that is asymptotic, but they're not asymptotic integrals. It's almost the word that we use is almost like it's almost like a comment on their behavior. Whether they were good kids or something. We don't remember. Improper. Improper integrals. Okay, that's an improper integral. Now, do you remember how we computed this? No. In fact, improper integrals was your first exposure to the word converging and diverging. That's where you learned that concept. Okay? So, if we're going to compute this improper integral, remember we did this. We changed this to a limit problem. And we got that. And then we computed that limit, and we said if that limit existed, the integral converges. If it didn't, the integral diverges. Remember that? Now this integral, because as b goes to infinity, the natural log of b approaches infinity, that integral diverges. Okay, the integral diverges. Okay, now let's go back over here to the area context. All right, let's go back over here to the area context. Now, funny thing is everything you guys just wrote down, you've already written down once before. That's okay. Go back over to the area context. What does that mean? The fact that we got infinity over there. What does that mean in the context of this area? That area is getting bigger, right? And that area is infinite, from 1 to forever, right? Does that make sense? Okay. So everybody's cool with that? Okay. Watch this. That's a 7. So I made a Riemann sum here that kind of looks like it would approximate that area, right? Would you say that the sum of all the areas of those rectangles, would you say the sum of the areas of those rectangles is greater than the value of the integral or smaller than the value of the integral? Greater. Why? Because they're above. Okay. The area of that first one right here is what? 1 times 1. What's the area of the second one? 1/2 times 1. What's the area of the third one? 1/3 times 1. What's the area of the fourth one? 1/4 times 1. What's the area of the fifth one? You see what I'm getting at here? What do you guys see? These each represent areas of those rectangles, right? If we do that forever, we know that because of that picture, that this right here, the areas of all those rectangles, is bigger than the actual value of the integral, right? But do these numbers look familiar? What are they? It's the harmonic series. So what have we shown? That if I add up 1/2 plus 1/3 plus 1/5 plus 1/6 plus 1/7 plus 1/8 forever, that's bigger than infinity. What? Yeah. It's bigger than something that diverges. So what does it have to do? It has to diverge. Okay? Since that integral diverged, the series diverged. Okay? So we just proved that that harmonic series diverged. And we also use what the integral test tells us. Okay, so what's the integral test? Let's write that down. That's crazy. Crazy town. So the integral test is this. So we're going to start with our unknown series. And we're just going to say let f of x equal be such that f of n equals a sub n. Basically, you're just saying we're creating a function out of the series. Okay? And then we'll just say if this integral converges, the series converges. Now that's not what we just showed with the harmonic. What did we show? If this integral diverges, the series diverges. Isn't that what we just showed? So let me show you how the first one kind of works. We'll just draw a quick picture to show you how it works. Okay? So let's say we have the same idea, right? And we've got this area. And we know that that area now converges, or that area is finite. We can do the same thing that we just did, but we create our sum this way. And do the, etc. Now, what do you notice about those rectangles? In the area of all those rectangles, they're less than the area under the curve. And if the area under the curve is finite, and you're less than something that's finite, then what are you? You're finite. Right? And if the area under the curve is approaching 7, and you're less than 7, well, guess what? You're not infinite, right? You're less than 7. Okay? So that's why the first one works. All right? What's the hard thing about the integral test? Doing the integrating. It's the stuff that you've already learned, right? And a spin-off of this, a spin-off of the integral test is the p-series test. Okay? This is like the Better Call Saul of the Breaking Bad show. Doesn't know what I'm talking about. You don't know what Breaking Bad is? The show Breaking Bad? Every one of you should watch the series Breaking Bad. It's like one of the best shows ever made on TV. It's unbelievable. The writing is unbelievable. It's kind of dark. But basically the premise of the show, if you've never seen it, is this guy is a high school chemistry teacher, and he hooks up with one of his former students, and they start making meth. And like, cause he's dying of lung cancer, and he's doing it to like get money for his medical bills and to help his family. It's unbelievable. I know it sounds terrible, but it's really, really good. But then there's spin-off series, you know. So this is the p-series test, this is the spin-off series, the spin-off test of the integral test. Do you guys remember the p integrals? Remember that? Sort of. Okay, so the p-series test is this. If you have a series that looks like this, 1 over n to the p. And you can start these at really anywhere greater than 1, but this converges if the exact same rules for the integrals. You know why you don't remember this? Because I never tested you.
I thought we could use it for the. We had like two problems, like with converting and
Yeah.
on the last page.
Oh, it was on the last page. Was that the exam or was that, what was that?
No, that was like the.
Oh, the integration test. Okay. It converges if p is greater than 1. And it diverges if p is less than or equal to 1. It's the exact same rule for the p intervals. Okay? So here's our two new tests that we've got in our little arsenal of tests. So let's do some quick examples of these. So how about this one? So what do you think? Why? That's a p series, right? I mean, that's just 1 over n cubed. It's a straight p. Okay? Nothing fancy. P equals 3. It's a p series. That's a converger. Okay? Here is another one. Okay, what do you think? Is that a p series? It looks like p. It even kind of smells like p. But it's not p. Why is it not a p series? The 1. Okay? The 1 messes things up. Now, next week, we're going to learn essentially a way to say, well, if it looks like p and smells like p, it pretty much is going to be p. Like, you're going to treat it like p. Like, same rule in life. If it looks like p and smells like p, treat it like p. Okay? But right now, we're gonna do this the long way. So what's our other way of doing this? Okay, let's run through the test. What's the nth term test going to tell you there? If I do the nth term test, the terms approach 0. That tells me nothing. Is that geometric? No. So what do I got next? The integral, because we already said it's not technically p, so we're going to do the integral test. Oh, okay, so let's do the integral test. So that's going to be from 1 to infinity of 1 over x squared plus 1. And we're going to compute that integral. Okay? So we're going to say that's the limit as b goes to infinity of 1 to b of 1 over x squared plus 1. I can tell you the hard part about the integral test. It's going to be finding the antiderivatives. What's the antiderivative of 1 over x squared plus 1? Well, it could be a trig sub. And if you do the trig sub, you're gonna get to the answer eventually. This also could be one that you just know because you know the derivative of the function whose answer this is. This is inverse tangent. If you do the trig sub, you're going to end up getting inverse tangent. So the inverse tangent of 1, my friends, is pi over 4. What's the inverse tangent of infinity? Where is the tangent undefined but positive? Pi over 2. Tangent of pi over 2 is undefined, right? Like, all right. And if we're in the first quadrant, we're at positive infinity. All right, so that's pi over 2. So pi over 2 minus pi over, well, it doesn't matter. This converges, right? I mean, yeah, that ends up being pi over 4, but who cares? This converges. So what does that mean? The series converges. Okay, so somebody's got to ask it. There's a question that I would think is on somebody's mind right now. What is pi over 2 minus pi over 4 ends up being pi over 4? What is that pi over 4? In that context of that interval, what does that pi over 4 mean? What? No, in the context of the interval. It's that area. That area under that curve is approaching pi over 4, right? What does that mean about that series? Does the series converge to pi over 4? Well, is the sum of the series, or what the series converges to, is that equal to pi over 4? Do you understand what I'm asking? Like, think back to this picture. We said the area was approaching pi over 4. Does that mean all of these add up to pi over 4? Not necessarily. Right? But pi over 4 is a cap, right? The answer to the sum of that series is not going to be any more than pi over 4. You see why? Oh, wait. I love how you just all wait. So here's our new paper. This is for this weekend. I would probably start doing these on a separate sheet. I mean, you're going to run out of room trying to do these computations on this paper. When you do the integral test, at least set it up. If you can't compute the integral, at least set it up. You're going to have some trouble because we forgot how to integrate. It's been a while since you actually had to compute something, right? Have a nice afternoon. Have a nice day. Have a nice Friday. What are you running? 4 by 8.
I love it. But I'm no longer shopping there because it's like, and I knew that when I ordered these. But I was like, I want plus cheese, but I can't do it anymore.
I know. Yeah, please. No. Yeah. I don't know that either. That's what's cool. So, I mean, the juice ginormous balls.
sure it was flat or not, so I didn't see that. I just thought it was an opinion question. So I just put the flag, sure. it's definitely not. So, you like some food? I have like 8 bags. Huh?
What's up?
What's up? Nothing. Jimmy! Congrats!
Yeah,
Like you knew yesterday, you didn't even say anything.
I know.
Like I had to hear from third parties. Jimmy got an appointment to West Point.
Yay!
Yeah, I just had to keep telling people. How did you find out? Well, I still don't know which nominating field I got it from because all of them contacted me to congratulate me. I think I got it. I would have found out from a phone call. I missed that call. And then I told them 2 days after I got an email, different person.
So like Congressman Turner call you or something?
I got called by state director from Sherry Brown.
So like you didn't talk to Sherry Brown necessarily, you talked to one of his cronies. Please say he was just calling. I mean, how many people have to call seriously? Like, how many kids in Ohio got appointments to us? You actually don't know that. I mean, I bet it's. Well, how many kids get into West Point in a year?
Over 1,000.
So if we just divide that by 50 states, that's what, 20 apiece? So Ohio probably has, so maybe 100 max in Ohio. That's, I guess. Where's West Point? In West Point.
What?
In West Point. It's in New York. It's like New York State. So if you if you're like in New York City, and you basically go straight north from New York City,
It's like an hour north.
yeah.
Isn't the actual place called just like the Army Academy or something?
What?
The actual name of the college, isn't it like Army Academy or something? Not
What's the United States military?
military.
The full name is the United States Military Academy.
And I didn't know this, but people can end up in the Marines that go to West Point. Is that true?
I think so. But
Yeah.
I don't think that's
Yeah, most people end up in the Army though. Like, because he'll graduate from there as like a commissioned officer. And we've had quite a few kids as of late go there. So I mean, Marie Dawkin, she went there. She graduated from here in 2016, I think. No, 17. 17, because she's graduating from West Point in a couple weeks. And then Evan Overholzer, you know him? He graduated last year. He's at West Point right now. I'm assuming, is he still there?
Yeah, he traveled.
What he did? What?
Yeah, he's still there.
What's that? Will Taylor graduated from here in 05. He graduated from West Point. I mean, he's actually. Will maybe. He graduated from West Point, and he may actually be finished with his military career. I don't know if he ended up staying in all.
The regional, or not, the district person, that, they have graduates around everywhere that help out people that are applying. So the person that helped me
Is what?
I think they were, it was either 05 or 95.
From Fairmont?
Not from Fairmont, but.
Oh, from West Point. Oh. Yeah, Will would have graduated from Fairmont in 05, graduated from West Point in 09. He was actually ran cross country at West Point, and he was going to. He was really close to becoming an Army Ranger, and like basically it came down to when there was one officer that for whatever reason didn't like Will, and like that kept him out. So I don't know if Will stayed in the Army and just pursued another path. But Marie Dawkins is going. She's doing engineering, like Army Corps of Engineers. In her job, she's going to Italy. She's going to live in Italy for like the next 4 years, I think. So it's pretty cool. All right, so this is what I want to do. So you don't need to write these down, but I want to know, like, if this were a quiz, how would you do? I want to know, do those three series converge or diverge? And in all honesty, you should be at the point where it would probably, for these three particularly, you should be at the point where it probably would take you longer to write down the problem than it would be to actually figure it out. Sometimes it takes a while to write down those signals. Very cool. Yeah. Is that up in the Okay, so ready? How would you do if this were a quiz? 100%? What would you do? Or a 33 or 66? What's number one? What's the first one? What do you think?
Does it diverge?
Why?
Because the limit as n goes to infinity is 1/3, so it never approaches 0.
What never approaches 0?
The values of the terms.
Thank you. So we do that limit and we get 1/3. Okay? The two things, you need to know what the 1/3 means and then what's the conclusion you can draw. Okay? The 1/3 means that the terms are approaching 1/3. And the conclusion that we can draw is the series diverges. Okay? Number 2. Why?
Because R, which is 3 halves,
It's geometric. Yeah, that diverges because it's geometric with R greater than 1. Yeah. Gary, what's the third one? Why?
because the common ratio less than 1.
So the third one converges because R is less than 1. Pi over 4 is less than 1. Yes, it's geometric also. Pi over 4 is less than 1 because pi is about 3-ish. 4 is about 4-ish. Okay, so how do we do? 3 out of 3? 100%? Okay, sweet. So we also had to, I wanted you to work on those two from the homework for the other day. Remember those? Bless you. So what was that first one, the number 3, Billy? Was it n, what over n? N squared minus 1, okay. So if we have these, so we can write that, yes? And then I told you that we want to break that into partial fraction. Remember that? Now some folks last year didn't remember how to do this partial fraction thing. Do you remember how to do it? Use that cover-up method. So the cover-up method goes like this. So I look at this guy here, n plus 1. I say, okay, what makes him 0? -1. So then I cover this up over here. I cover up a -1. I cover this up, and then I plug in -1 for n. So what do I have? 1 over -1 minus 1, so that's -1/2. So that's A. And then B, 1 make him 0. So I go over here and I say, okay, 1 over, oh, that's positive 1/2, yeah? And then I'm going to do this just because I think the magic is going to reveal itself a little easier. I'm going to rewrite this 1/2 over n plus 1 as -1 over 2n plus 2. Because that's the, really the same thing as that. I mean, if I write that 1/2 like this, then I get that. And then how would I write the other one? 1 over what? 2n minus 2. Yeah? Okay. So you ready for the magic? Where did this series start, Billy? 2, right? That's what I thought. Okay. So let's do n equals 2. So when I get n equals 2, what do I get here? 2 times 2 is plus 2. So that's -1, 6. Plus 2 times 2 is minus 2. -1, 6 plus 1/2. That's my first term. I'm just going to leave it like that. Next term, n equals 3. 2 times 3 plus 2, -1/8. Plus 2 times 3 minus 2, so -1/8 plus 1/4. Next term, what are we on? n equals 4. 2 times 4 plus 2, 1/10, -1/10. Plus 2 times 4 minus 2, 1/6. Let's do another. N equals 5. 2 times 5 plus 2, -1/12. Plus 2 times 5 minus 2. Let's do one more. Anybody see the magic? You might not be looking for the magic. What's the next one? -1/14 plus 1/10. Okay, check this out. Ready? Yada, yada, yada. Dot, dot, dot. Look at that. Here I got a -1/6. But then down here I got a positive 1/6. Here I got a -1/8. And then down here I got a positive 1/8. Here I got a -1/10. And then a little bit down the road I got a positive 1/10. What's going to happen to the negative 112? It's going to get canceled out by the next guy here. What's going to happen to the negative 114? It won't get canceled by the next one, right? What happens to all of these terms after these first two? They go away, right? So just left with 1/2, 1/4. So what is that? 1/4 and 1/2. Today adds up to 3/4. Right? This is called a telescoping series. Telescope. And it's called a telescoping series because it's named after those old school telescopes that you kind of see on cartoons, like they expand and they collapse in on each other. You know what I'm talking about? You don't really see those too often, but back in the old school days. Okay, this series kind of collapses in on itself. Telescopes. Okay? The one after that, I think when you do the math, you're going to end up getting, I think, this. You're going to get the problem at the bottom. You get 1/3. What are the two fractions? N and what? Yeah. And then negative 1/3 over n plus 3. That's what happens when you get a and b. And so that's going to be 1/3n minus 1/3n plus 9. That one takes a little bit longer to telescope. Before you start to see it. But it will. Telescoping is hard to recognize. Okay, and you have to write out a bunch of terms to actually find out what it sums up to. Soon, maybe not today, but soon, you're going to be able to look at this and just tell me that it converges. You won't even have to do anything. Okay. So how do you feel? You feel good? Oh, is this so good? That's who you're looking at.
The easy way to tell if it converges or not is just to plug in like some insane number, like 1 million or something, and see what it comes out to be. See if it's going to 0 or not.
Well, plug in 1 million into what?
And the 1 millionth term in the series, see what it is.
Well, I'm not sure if I want to answer that question. Maybe you guys should answer that question. What happens if you find out that the 1 million? You don't even need to do that. You can just take the limit. But what happens if you see? What happens if you do this? You're just trying to avoid all the work, right, Alex?
No.
What if I give you this? Here's one. Does that converge? So, Alex, I think you're doing this. Right? But this is the importance of knowing what the limit answer means and what you can conclude from it. And the conclusion from the limit is tied to why you did the limit in the first place. What does that answer 0 mean?
The terms are approaching 0.
The terms are approaching 0. What can we conclude? Can we conclude from that? Nothing. Because just because the terms are going to 0 does not mean the series converges. Because the nth term test says this. If the terms are not going to 0, the series diverges. Right? That does not mean the same thing as if the terms are going to 0, the series converges. Doesn't mean the same thing. It's like a rectangle square kind of thing. Right?
What would be an example where it doesn't converge when they're going to 0?
That one. We're going to prove that this was the example that we're going to start off by, the new stuff with anyway. But that series right there, which if I write out terms of this series, 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5 plus 1/6 and so forth, that series diverges. The sum of that series is infinite. And yes, the terms are going to 0. They're just not going to 0 fast enough. That's really the gist, okay? And we'll see that later down the road, but they're just not going to 0 fast enough, okay? So when you do the nth term test and you find the limit of the terms, and what's happening to the terms, and you say, oh, the terms are approaching 0, that means nothing. Okay? You're not done. You got to do something else. Okay? Samuel, what's the question? You what?
No, never mind. I was thinking something, but
You changed your mind?
yeah, like realized that there's nothing else. I was thinking maybe this portion of the Calc series was like n plus 1 over n, but it's not true at all, like ever.
Yeah, it's not.
I don't know why I would think.
So if you watched the video from a couple days ago, you actually would recognize that series. It even has a name. This series is called the harmonic series. Okay? I talked about that in that video. And we even use that as an example of where the nth term test fails. Like, the nth term test tells you nothing here. Okay? Well, what we're going to do right now, friends, is we're going to prove that this diverges. Okay? We're going to prove that this diverges. All right? And in the process of proving that that diverges, we're going to learn 2 more tests. The integral test and the p-series test. Okay? So we'll just leave that up there. All right? And so our goal is to prove that that diverges right now. So here's how we're going to do it. You ready? This is slick. You might like this. I'm going to consider this function. That was embarrassing. I can't even stand how that looks. I'm going to consider this function. Is that better? Is that better, Joe? That looks better. I'm going to consider that function. All right? So, what would that mean in the context of that graph that I just drew up there? Could we interpret that integral as something having to do with that graph? How could you interpret that integral with that graph? Is it an area? Or could it be an area? What area is it? Yeah, it's this area here starting at x equals 1. Right? And it's this area here forever, right? Right? Forever, down the river. Now, we learned a way to compute those areas or those integrals where we have infinities in the limits, in the bounds. You remember what those are called? It's been a while. What are those intervals called where we have infinities in the bounds?
Isn't it like up and down?
They're not root integrals. They're improper. Yeah, they're improper integrals. But we learned how to compute those guys. In fact, you were tested on it. You're tested over all the different techniques of integration. The last page, there were 2 problems on there. They were improper integrals. Okay? But how do we compute one of these guys? Remember? Well, I'll tell you. The convention is you change the infinity to a b. I don't know why we use b, but we just do. And then we just do this as a limit problem. So that ends up being the natural log of x, and we're going to evaluate that from 1 to b. So that's the natural log of b minus the natural log of 1. Right? And what's the natural log of 1 is 0. And then you compute that limit. So, okay, what happens to the natural log of b as b goes to infinity?
Log of p goes to infinity.
Yeah, it goes to infinity. Okay? And in fact, when we learned improper integrals, friends, this was the first time you ever heard the words converging and diverging. Okay? This improper integral diverges because that limit was infinite. All right? Is everybody with me?
Any series where the equation, or the assumption for any function where the series has a diverging.
Yes, that's the integral test. You're about to state the integral test. Yeah.
No, I wasn't saying before to find the series, but like if the or if the series goes to or isn't unbounded, would that mean that your goal is always unbounded or not?
It's the other way around, but yes. Yeah. That's exactly right. So what does that infinity mean in the context of that area? What's that infinity mean in the context of that area? There isn't. Okay, you guys got that? Okay. That's important to understand. All right, so I'm gonna draw that area again, but I scribbled in it, so I'm gonna draw it again. Is that okay with you? So I labeled some points on the x-axis. Is that okay? Is that okay, Karen?
Yeah.
Okay, good. So that's kind of like we're almost setting up like a Riemann sum there. But if I were just to calculate the areas of those rectangles and add them up, would it be bigger or smaller than the area under the curve? Guys, that's not a hard question. Billy? Bigger, right? The area of all those rectangles, we'll add up areas of all those rectangles, it's going to be bigger than the area under that graph, right? For sure. For sure. Right? What's the area of the first rectangle? This is 1 over x, right? What's the area of that first rectangle? Well, it's this height times 1. It's 1. What's the area of the second one? 1/2. What's the area of the third one? 1/3. What's the area of the fourth one? 1/4. And the fifth one? 1/5. And the sixth one? 1/6. And the seventh one? 1/7. And the eighth one? 1/8. And so forth. Right? So if I do this forever, the answer to this is bigger than the answer to the area under the curve. Yes? But what's the area under the curve? Infinity. Infinity. Infinity, right? So the answer to this is bigger than infinity. It's greater than something that's infinite, which means it's infinite. Do you recognize these numbers, people? There are these numbers right here. This is the harmonic series, right? We just proved that it diverged by looking at the area under that curve. Okay? Now Samuel started to see this initially, and so he tried to summarize this. Well, the summary of this, so does this work for any kind of function? The answer is, yeah, kind of. The summary is this, and that's what the integral test is. So the integral test says if we have a series, our unknown series, and we have a function, and our function at n is equal to our series at n. Okay, now technically speaking, the function's got to be decreasing, but if it weren't decreasing, then the series wouldn't diverge anyway because its terms would be going to 0. But the integral test says this. There's two parts to it. The first part is if the integral diverges, the series diverges. They do the same thing. And second, if the integral converges, what do we do? Or what do we say? The series converges. So you saw pretty clearly why the first one worked, right? We just did that. Why does the second one work? Okay, why does the second one work? You do almost the exact same thing, but you say this. We're just going to draw a general graph so you can see it. Okay, let's say the area under that curve is finite. It converges, right? Let's say that from here to infinity. If we do the same thing that we did a second ago, but we do it this way. What do you notice? The areas of all those rectangles, if I add them up, it's going to be smaller. So I just basically would do the exact same thing, set up a scenario where the areas fall below. And I'm saying, oh, this is less than something that converges. Therefore, you must converge. Exactly. So if you're greater than something that diverges, you diverge, or if you're less than something that converges, you converge. All right? Now there's a spin-off of this. A spin-off. You guys know what a spin-off is? Like, what's a spin-off TV show? Like, you know what that means? Now, I was shocked at the number of kids in my last grade class that had never seen Breaking Bad. Anybody ever seen Breaking Bad? You're the only one? I saw one episode?
It was boring.
You need to watch more than one. Was it the first one?
Yeah.
Oh, you definitely need to watch more than one.
I watched the
By the fourth one, you'll end up binge watching the entire series in like 2 weeks. Like, the premise of the show Breaking Bad, in my opinion, Breaking Bad is probably one of the top 5 television shows ever produced. Okay, like the writing is unbelievable. It's kind of dark. Now, and I'm saying dramas, not because you can't just put everything in one basket. I mean, there's too many genres. Like, it's not a comedy. Like, I mean, there are funny parts, but it's not a comedy. So it's a drama. So I'm going to say top 5 dramas of all time. It's kind of dark. There's a lot of terrible things that happen, and these people are terrible human beings. But the premise of the show is it's a high school chemistry teacher gets diagnosed with lung cancer, and he doesn't have a lot of money, and so he hooks up with one of his former students, and they start making meth. And to make money. He's trying to make money for his family. That's kind of the gist. But it's much larger. Well, then there's a spin-off show called Better Call Saul, which is a spin-off of Breaking Bad. So I highly recommend watching Breaking Bad. It's a great show. But you gotta watch more. You totally gotta watch more. So what's the spin-off of the integral test? The spin-off of the integral test is the P-series test. Okay? The P-series test, if you remember, we talked about P integrals back in the day. The P integral or the P series test goes like this. If your series is of this form, 1 over n to a p, n to a power, any power you want. Okay? A series of this form converges if p. Anybody remember what the rule was for integral tests? P is greater than 1. Or not greater than or equal to, just greater than 1. And it diverges if P is less than or equal to 1. That's the P series test. So now we've got 2 more tests sort of in our arsenal. All right? We have 2 more tests in our arsenal. Now let's do some problems. Like, look at some examples of these babies. P-series test is by far the easiest one ever. What makes the integral test hard? You have to compute integrals. Nobody wants to do that. So does that converge or diverge? Okay. What are the terms doing in that series? What are the terms doing? Billy, what are the terms doing? They're going to 0. Does that tell you anything? Nope. But that series is a P series. Isn't it? What's P? 3. So what is this one guy? What are we going to do? So he does what? Converges. Okay. What about these? Maybe you don't see it, but that's the same thing, isn't it? What does that do? Diverges. It's a p-series. P is 1/2. Diverger. Okay, what about this one? Is that a p-series? What do you think, Billy?
I'm gonna go with yes.
You're going to go with yes?
Yeah.
Is it of the form 1 over n to the p? Well, how are you going to reconcile the 1 in the denominator? It's not 1 over n to the p plus some number, right? I mean, it kind of looks like a p-series. It smells like p. It's not technically a p-series. Okay? It's not technically a p-series. So we're going to do the integral test. Well, but maybe, actually, let's run through our other test. Is it geometric? No. Can I use the nth term test? What are the terms doing? They're approaching 0. Does that tell me anything? No. So where am I now? Well, we already know it looks like a piece, but it's not a p. So we're going to do the integral test. So we're going to do this. We're going to compute that integral. Oh, God. How do we do integrals? We haven't done those in so long. What do? We got to find the anti... Oh, well, first let's write it as a limit problem. I can tell you right now, when you do the integral test, finding the integrals are actually going to be the hardest part of the integral test. I haven't done it in a while. Oh, man, you might have to integrate by parts. Oh, gosh. Might have to do a U sub. What do? How do you do this integral? 1 over x squared plus 1. Now, I would just love it if you just know the antiderivative of 1 over x squared plus 1. If you don't, you'd have to do a trig sub. But if you just know the antiderivative of 1 over x squared plus 1 is inverse tangent of x, it's so much easier to do, right? Should we know that one? Yes. So what's the inverse tangent of 1? Pi over 4. And what's the inverse tangent of b as b goes to infinity? Where is the tangent approaching positive infinity? Pi over 2, right? Now, it turns out, so the answer to this is pi over 2 minus pi over 4, which ends up being pi over 4. But guess what, kids? This integral converges. So the series converges by the integral test. Okay? Now, I will tell you that next week, early next week, we won't necessarily do that problem with the integral test. Because we're going to learn a rule that basically says if it looks like P and smells like P, treat it like P. Like that's how you should operate in life, right? You come across something that looks like P, smells like P, you're probably going to treat it like P, right? Here. First 6 of these, oh baby. Can we do the integrals? Can we do the integrals?
Are we gonna follow this?
Yeah, you're going to do all these because some of them are going to take you 2 seconds. I would recommend not doing these on this paper. Like, you're not going to have enough room. That's what I recommend. Bon weekend. I will see you later. I'll see you on Monday.